Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about deriving expected utility theory. Sorry, that was theory. My name is Rick and my co-teacher is Christoph. Let's begin with an outline of what we want to do today. First, we want to talk about lotteries. You'll see why in a minute. And then we want to derive the concept of utility. Next, once we have that, we'll derive the more general result of expected utility theory. Then we'll talk about some implications, and I'll finish off with a note about how you can rescale utilities. So that might not seem like too much, but it's actually quite a bunch of work to do. So we better jump into it and pay attention and follow along carefully. I'll try not to lose you. We'll start with lotteries. And the reason we're doing that is because expected utility theory is all about how to make decisions when outcomes are uncertain. And lotteries are a convenient framework for introducing this uncertainty. Maybe I should discuss our motivation a little bit more. Why are we even talking about expected utility theory? We'll get to what it is and how it's useful. But the reason we're talking about it is because it plays a big role in game theory when you're dealing with certain kinds of Nash equilibria and certain what you call mixed strategies. So like a mixed strategy, in a lottery, you can have multiple possible outcomes. The outcomes are just determined by chance. So the way I'm going to denote that is by drawing a die. And the idea there is that you're rolling a die to see what the outcome is going to be. And you might have, let's say we have 3 possible outcomes. And each one maybe has a certain probability of occurring. So let's call that probability of A, and PB can be the probability of B, and PC the probability of C. So our outcomes are A, B, and C. You notice that looks like a decision tree, but notice that the outcomes are determined by chance instead of by choice. And that's why I'm drawing that die there, to just emphasize that. So some properties here that you should think about. The P's are probabilities, which means that they all lie between 0 and 1, and they have to add up to 1. Which also means that they're exclusive options. You can take the path to A or B or C, but not any 2 or 3 of them, just 1. So that's a simple lottery that you could imagine. And if you end up at A, then that's the outcome from that lottery. Let's make that a little bit more complicated. We could have a case where the branches are nested, and the normal, let's call them the and or rules of probabilities apply here. In fact, the branches, each of the let me say the sub-lotteries are independent, and the choices at each one of those sub-lotteries, each node, are exclusive. So these and or rules are actually quite simple. And means just multiply the probabilities, whereas or means add the probabilities. Let me give you an example how that works, just so you can see for yourself. Let's say we have a nested lottery. So after the first die is rolled and the outcome is determined, another die is rolled. And let's say there's again 2 possibilities. And let's say we label the outcomes A1, A2, and A3. And for fun, let's say this middle one here is again A2. So it's the same outcome on either of 2 possible paths. Let's also define our probabilities for these different paths. Let's call this PA, and if that's PA, then this is the complement, 1 minus PA. And let's say this is PB, so this is 1 minus PB, and up here we have PC and 1 minus PC. Okay, my point is that we can use these rules for and or to simplify this lottery and turn it into a simpler lottery, and I'll just use that to show that these are equivalent. And the other lottery would look like just the one random number generated and 4 possible outcomes. Correction, I wanted to show you the case where there are 3 possible outcomes. That was kind of the point of doing this. And those outcomes are A1 or A2 or A3. So what we're talking about here, let me just emphasize this, is we could be going along this path and up here, which would take us to A3, or we could be taking the bottom path here and the bottom path here, which would take us to A1, or we could take the top path, then the bottom path, or the bottom path, then the top path. Either of those paths take us to the outcome A2. It's just a matter now of figuring out what the probabilities are that make these 2 lotteries match up. And as I said, you just use the and or rules. So to figure out what the probability of ending up at A3, the top branch on the right, is, it's just the probability of taking this path, which is PA, and then taking this path, which is PC. So the probability of doing both is PA times PC. And likewise, for the bottom branch, it would be 1 minus PA times 1 minus PB. And what about the middle branch? Well, now there's 2 ways to get there. If we take this top branch, then it would be PA times 1 minus PC to get here. Or we take this branch, which is 1 minus PA times PB. And because these are exclusive options, we just add them together. So it's just plus 1 minus PA times PB. And that's it. You should check for yourself that this is an exhaustive description of all possibilities. The way you can do that is by making sure that these probabilities all add up to 1, just like we said up here, that all the branches, the probabilities of all the branches out of a node have to add up to 1. So all the branches out of here have to add up, the probabilities have to add up to 1. Check that for yourself. Okay, that's all that's required for understanding how lotteries work. So we can use that now in trying to derive utility, the concept of utility. I'll explain what that means in a minute. So let's start by considering a case where there are, let's say, n outcomes. And we'll call them, let's say, A1 up to AN. And let's also say that AN, the last one, is most preferred, or the best possible outcome. And A1 is least, or the worst possible outcome. It'll just help us when we're organizing our thoughts a little bit. We don't put any other constraints on how we prefer A1 to AN. It's just that we need some of them to be better than the other. So they could all be the same except for one of them, or they could all be different, however you like it. But A1 needs to be worse than AN. That's kind of our criteria. So what I want to do, let me just paint a little bit of a picture of where we're going with this. We're going to show that the outcomes can be assigned numbers, and the preferences can be ranked by these numbers. So what I mean is bigger numbers indicate a stronger preference. Essentially, that is our definition of utility. It's a measure of preference. And by measure, I mean a quantitative amount that you can assign to something and say, this is how much I prefer this thing. So make sure you have a sense of what the word utility means. We'll use it again and again. Okay, to actually derive the concept of utility, we need to work with lotteries. So what I'm going to do is let's create something, let's call it an extreme lottery. And that's a lottery that will pay out the best outcome or the worst. We'll call this, let's call it X of P. And what I mean by that is a lottery that gives outcome AN, that was our best outcome, with probability P. Otherwise, it gives or pays out outcome A1, which is the worst possible outcome. So you should notice that x0, which means the P, the probability of getting the best outcome is 0, is the same as just A1 itself. And on the other hand, x1, so we get outcome AN, the best outcome with certainty, that's the same as that best outcome AN itself. That's pretty obvious, right? Let's draw our tree for this, our lottery tree for this. So there we have a roll of the dice to see what the outcome is. And with probability P, we get the good outcome, AN. That's our best outcome. And with probability A1, with probability 1 minus P, we get outcome A1, which is our worst possible outcome. So that's why I'm calling it an extreme lottery, because it's, of all the possible things you could win, it's going to be either the best or the worst. Now, we can use our concept of indifference to find a lottery that matches every outcome. What I mean is that for every one of these outcomes, let's say, call it AI, where I is one of them, there's a lottery, X, and let's call it this. So that was X with probability UI. That makes the player if indifferent, meaning that the outcome AI is equally preferred as the lottery with probability UI. On the one hand, we might have like a null lottery, AI, where just drawing this straight line just means that there's only one outcome. It's a sure thing, a certain outcome. Or on the other hand, there could be this lottery which pays AN with probability UI. Otherwise, with probability U1 minus UI, it pays A1. And these two things can be set to be equally preferred to each other. So if you choose the right value of UI, then the player is indifferent to choosing one or the other, has no preference, doesn't prefer AI over the lottery or the lottery over a certain outcome AI. And I think you can see that, at least if you think about the special cases. A1 must be preferred equally to X0. And that's just because if X is 0, if P, I don't even mean P. If U is 0, so the probability U1 is 0, then that means that in this general lottery, or let me draw it down here. So in this general lottery, U1 is 0. So we're not getting this top branch. We are certainly getting this branch. And so there really is only one outcome. And so this lottery, if U1 is 0, then it's exactly the same outcome as just getting A1 itself. So that means right away that U1 has to be equal to 0. And by the same kind of argument, the best possible outcome is indifferent, or a player would be indifferent to getting either the best possible outcome with certainty or playing the lottery, but where the lottery is rigged, so they are certain to get that best possible outcome. So we have well-defined values for these special cases. And I hope you can see that for any other case where the outcome isn't as good as AN, so let's say any kind of other AI where it's not as good as getting AN, but it's better than getting A1, then the player is going to have some kind of UI, some kind of probability of getting the top branch, where they'll be indifferent to this lottery versus this sure outcome. Okay, and the next piece of reasoning that we need is that between two possible lotteries, let's say X of UI and another lottery, this one, X of UI, would be preferred to another lottery, let's say x of uj, if and only if the probability of ui is bigger than the probability uj. So this is just saying that the lottery that has the bigger probability of paying the best outcome is preferred. If that's the case, and the lottery is preferred, then the certain outcome, AI, would also be preferred to the certain outcome, AJ, if and only if these probabilities UI, or this probability UI, is bigger than the probability UJ. And remember, in this context, the U's are the probabilities of the lotteries that make the player indifferent. So what we've just done here is come up with a number, this probability UI, that kind of tells us our preferences. If UI is bigger than UJ, then we should prefer outcome AI to AJ. And so every outcome has an associated number. We've just sneakily come up with a utility. So every outcome AI can be assigned a value, UI, which is the probability of the lottery, that extreme lottery, which gives the same preference as that outcome AI. And of course, a larger utility means a stronger preference. And it's important to note that every person can assign different utilities to the same outcomes. This result just shows that there are numerical utilities. So you could have two people, one who has one set of preferences and the other has exactly the opposite set of preferences. So what the first player would define as being the best outcome with U equal to 1 would be the thing that the other person defines as the worst outcome, having U equals 0. Let's go through an example. Let's say that you prefer an apple, let's say that's A, over banana, there's our B, and that over carrot, so that can be C, and let's have one more, over dirt. Yeah, okay, that works for me. Over dirt. Then if we want to look at our preferences here and compare the certain outcomes to the lotteries, the extreme lottery, well, we already know that the apple is the most preferred thing and the dirt is the least preferred thing, so we've got our best and our worst. And we want to compare that to some certain outcomes. So let's say a banana as a sure thing. What is the lottery that makes us indifferent? So the lottery we're thinking about is our best outcome versus the worst outcome. And for the banana, let's say there's some probability UB and 1 minus UB of these respective outcomes. And with that lottery, this player, or you, would become indifferent to these two choices. On the other hand, let's look at the sure thing of getting a carrot or another lottery. And again, the lottery outcomes are going to be either the best thing, the apple, or the worst thing, dirt. And we're going to be indifferent if that lottery pays out the apple with the probability UC. Otherwise, it pays out dirt. So we already worked out that the utility of the best thing is 1. So that's the utility of the apple. The utility of the worst thing, dirt, is 0. So we know that the utilities of the other two things have to be between those. And we know that because we prefer the apple more than the other outcomes. So UB can't be as big as 1. And likewise, UC can't be as big as 1. But it has to be bigger than 0. Both of them do, because we prefer both of them over dirt. And finally, let's think through the reasoning here before I get to the final result. So we have a banana, which we have equal preference to as this lottery. We know we like the banana better than the carrot. The carrot we have equal preference to as this lottery. We know we like lotteries better if they have bigger values of the paying out, our probabilities of paying out the best outcome. So if this is better than this, then this lottery must be better than this lottery, which means that UB has to be bigger than UC. Okay, so that tells us that for every certain outcome, if we can state what our preferences are, then we can assign a utility to every certain outcome. Now let's move on to expected utility theory, where the outcomes aren't certain. So the challenge now is, how do we choose between uncertain outcomes? And to work through that, let's create a new lottery which can pay out all possible outcomes. We'll call it L, and for the lottery L, we have to indicate what the probabilities are for all possible branches. So the probability of getting outcome 1 or outcome 2 all the way up to outcome N. And that will be a lottery that pays out outcome AI with probability PI. And of course, we must have that P1 plus all the other P's up to Pn have to add up to 1. So let me draw what this lottery tree would look like. So we have our source of randomness, which can give all sorts of different outcomes, and the outcomes can be A1 and then A2, A3, all the way up to AN, and the probabilities of each of these branches are just the associated P. So P1, P2, all the way up to Pn. So you can imagine that there's more branches here, and I'm just not filling them in. So in this context, when we're trying to figure out how to choose between uncertain outcomes, the problem really becomes how to choose between any two lotteries. So we might have a lottery P1 to Pn, and we might have to choose between that and another lottery, which maybe is Q1, Q2, Q3, so on, up to Qn. And we've got all these probabilities, P1 to Pn and Q1 to Qn, and we have to decide how to choose between these two lotteries. To do that, we can recall what we already discovered for certain outcomes, which is that every outcome AI, it's already the same as or equally preferred, so it effectively indistinguishable from a lottery. I'll say it's already paired with an extreme lottery, X, with probability UI. So this lottery here, we can redraw with substituting the lottery's X of UI instead of the certain outcomes AI. So it starts the same. There's a probability of Pn of going to the top branch, P1 going to the bottom branch, and there are all these other branches in between. And for each one of them, we replace the certain outcome with the probability. And the probability is represents a new lot, the extreme lottery. So it was UN chance of paying out AN and 1 minus UN chance of paying out A1 for the very top case, and for the very bottom case, probability of U1 paying out outcome AN, and 1 minus U1 of paying out the worst outcome, A1, and all the other outcomes in between would also have lotteries. And this is where we start to apply the rules of probability that we talked about in the beginning. Because it would be nice to simplify this lottery tree and get rid of the sub-branches. So we can do that by applying what we call the AND rule. And let me show you how that works. So the top branch here with these two possibilities becomes two separate branches with outcomes either AN or A1. And the probabilities are just given by Pn times Un to go to the very top of the tree, or Pn times 1 minus Un to go to this outcome. And the same reasoning goes for all the intermediate branches. And I'll just draw the very bottom one, which again becomes two separate branches with outcomes AN and A1 again. And the probabilities are P1 times U1 to get the AN outcome, or P1 times 1 minus U1 to get the worst outcome. And again, remember there's all these other possibilities in between. In fact, there would be 2n possible outcomes. Okay, so that's cool. But we can go a little bit further even because we're getting a lot of redundancy. For every one of these branches, let me say it this way. There's an AN here, there's going to be more ANs here, and an AN at the bottom here. In fact, there are n duplicate outcomes that pay out AN, and they're all exclusive. So we can apply our OR rule to bunch them all together. And we come up with a new lottery, which is equivalent to the first one and the second one that we've drawn already, but it just has two branches. It either pays out AN or it pays out A1. And to get the probabilities, we just apply the OR rule, which means we just add up all the probabilities of the various branches. And if we look at those branches, there was a P1U1, and then a bunch of other ones, and in the end a PNUN. And on the bottom, it's just the other branches, so a P1 times 1 minus U1 plus all the other probabilities plus PN 1 minus UN. Now you should, again, check this for yourself. Take all of these, add them to all of these, and satisfy yourself that all of this adds up to 1, which means that one of these outcomes is chosen, but not both. So what have we done here? What we've just done is shown that any general lottery can be rewritten as one of these extreme lotteries with specially chosen probabilities for the branches. Or in other words, some lottery L1 with probabilities P1 to Pn gives us indifference versus an extreme lottery with probability, just one probability, that is the sum of all of these, P1U1 plus all the other PIUI up to PNUN. Another piece of information we need here, we already saw that for the extreme lottery, higher probability is preferred. Meaning X of P is preferred over X of Q if and only if P is bigger than Q. So now we have these sums here to compare instead of just single numbers P and Q. But the principle is the same. Given two lotteries, L of P1 to Pn, that will be preferred over another lottery, L of Q1 to Qn, if and only if P1U1 plus all the other PIUI up to PNUN is bigger than Q1U1 plus Q2U2 plus so on up to QNUN. So now we have a way of comparing two lotteries. So two situations where the outcomes are uncertain. We know what the probabilities are of the various outcomes, and if we know how we value each of the certain outcomes, the AIs, then we know how to value this probabilistic lottery. And if we interpret these UIs, U1 to UN, as utilities, then what we're really just comparing here is the utility weighted by the probabilities, and the utilities here weighted by their probabilities. And that's it. We just did it. We basically have defined expected utility, which is the sum of the utilities for the various outcomes, weighted by their associated probabilities. And we could write that as EU, and then for any given lottery, let's say L P1 to Pn is equal to P1 U1 plus P2 U2 plus so on plus Pn Un. And this is an important concept. Take note of it. Remember it. So just to sum up, any uncertain outcome, let's say a lottery, can be assigned an expected utility based on the probabilities of the outcomes and how utility is assigned to those outcomes. And choosing the highest possible expected utility reflects preferences. So you should choose the thing that gives you the highest expected utility. So there's some important implications to all of this. The first one being that the derivation that we did here is effectively an informal proof. And what I mean by that is some very smart guys, von Neumann and Morgenstern, formally proved this exact result using a set of axioms. And those axioms I've kind of tried to express in this presentation in a kind of a natural way so that they make sense to you and you can decide whether you accept them. And if these axioms, or let's call them assumptions, and the steps I've taken are acceptable to you, then this conclusion just follows. So it's inescapable in a sense. So that's a kind of a powerful thing to say, that if you accept this argument that I've presented, then it tells us how rational individuals must behave, i.e. how they must make choices in situations like these. And that's kind of cool to me. Another implication that you should think about, and I mentioned it a little bit earlier, is that what we've done here is only to show how to make a choice after the utilities are assigned. And it doesn't say anything about how to choose those utilities themselves. So they just come from personal preferences. Okay, so that's how we derive expected utility theory. I want to bring in one other concept, and that is about rescaling these utilities. So again, expected utility tells us to maximize this thing, expected utility, which is the sums of the utilities weighted by the probabilities. And you'll recall that in this derivation, we assigned particular values of the utilities to the worst and the best outcomes. Those were U1 had 0 utility, and UN, the best outcome, had 1 unit of utility. But I want to make the point here that we can rescale that. They don't have to be 0 and 1. We can choose a rescaling factor. Let's call it M, and it has to be bigger than 0. And we can also choose a shift, how much we shift the utilities by amount B. And so what I have in mind here is that we're mapping our original expected utility onto some new, let's call it EU prime. And it's just going to be a linear transformation. So there's going to be some intercept B, and then it's going to be a straight line relationship with slope M, and then it'll be times EU plus B. And just to emphasize this, we have a slope M, and it has to be bigger than 0. So we could have this new expected utility, which is shifted and rescaled. And it's just m times the original EU plus b. And let's see what happens when we plug our original EU in. So it's m times p1 u1 plus so on, all that plus b, which we can pull out the p1s. Maybe the probabilities of the outcomes are just what they are. We can't change those. So we pull them out, and so let me write this as m times the sum of pi ui plus b. And the trick here that I want you to see is that I can multiply b times the sum of pi because the sum of pi is equal to 1. So really I have multiple sums here, and I can group them together now to do a sum of m times pi ui plus b pi. And now I can pull out the pi, so that's a sum of pi times m ui plus b. And that really is just p1 times some other u1 prime plus all these other elements up to pn times un prime, where each of them, ui prime, is the old utility rescaled, m times ui plus b. Sorry about having to throw the math notation in there. I was trying so hard to avoid it. Not for any particular reason. It's just I hadn't introduced it up till now and seemed like a waste to have to throw it in at the last minute. But I realized I was going to make a mistake if I didn't do that. So what I'm saying here is that we can rescale the utilities, and if we do that, then our expected utility changes from EU to EU prime, but our preference ordering doesn't change at all. Whatever preferences we had are all in the exact same order as they were. And so we haven't changed our preferences at all when we've done this rescaling. The only constraint on that is that m, this factor, has to be bigger than 0. If it was smaller than 0, then effectively we would be reversing our preferences, and that's we can't do. So the point of this exercise, this little section here, was just to show that we can multiply utilities by any positive factor, m, and we can add any amount, b, to the utilities without changing the preferences. And the only constraint there is, well, besides m being positive, is that we just have to do this rescaling for all of a player's utilities in the same way. So if we want to rescale ui, we have to apply the same m and the same b to all of a single player's utilities. So whereas we originally had u1 equals 0 and un equals 1, those are not important restrictions. All we need is there has to be a lower bound and an upper bound, a best and a worst, or I should say a worst and a best outcome among the choices that we have. And we can assign those any utility we want. Basically what we're saying is that the units of utility are not important. So we could, I don't know, if we were talking about money, we could talk about different currencies, whether it's dollars or euros or francs or pounds or what, yen, and that doesn't matter. And whether we add a certain amount or subtract a certain amount, as long as we do it consistently for all the utilities, for example, in a payoff matrix, then it doesn't matter because it doesn't change the order of the preferences. Okay, I think I've harped on about that long enough. So let me just summarize. So what we did here is we derived expected utility theory. We did it by first coming up with kind of a formal definition of what a lottery is. And from that, we were able to derive the concept of a numerical utility for certain, sure outcomes. And then using that, we were able to derive expected utility theory, which just says that we should behave in such a way as to maximize our expected utility when we have uncertain outcomes. We talked about a few of the implications, and we talked about how we can rescale utility without it affecting our preferences or how we map our preferences onto utility. Okay, so that's all for this lecture. Thanks for watching.